Right, hello grade 12s. We are still busy with the counting principle. Specifically, this video is going to deal with certain problems we might have with trying to use factorial notation or even the permutations that I taught you about in the previous video. Okay, so first situation we have to look at is the following. Ask yourself this: is repetition of elements allowed or not? This becomes incredibly important because everything we've done so far in these probability problems have said that repetition is not allowed. So whenever we spoke about people, like the 8 swimmers jumping into the swimming pool, swimming in those 8 lanes, you can't clone a person. So you can't use the same person twice. You can't repeat the element. But there are certain situations we are perfectly allowed to repeat an element. So let's look at this example. If you have to create a 5-digit PIN code using the 10 available digits on a PIN pad, so your 10 available digits on a PIN pad, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And you want to create a 5-digit PIN code. The first question, how many PIN codes can you make if repetition is not allowed? Now this is the problems we have been dealing with up until now, where we are not allowed to repeat any of the elements. Each element, once it's been chosen, is no longer available for choice. It's over, it's done, can't use it. So if repetition is not allowed, then you are saying I'm choosing out of the 10 available digits, I'm choosing 5. So we can use that 10 permutation 5, or I can just go and say 10 times 9 times 8 times 7 times 6, which is then I have 10 digits available for the first one, I've got 9 for the second one, then 8 for the third one, 7 for the fourth one, and then 6 for the fifth one. So I can either do it manually or I can use that permutation button. So I can say 10 permutation 5, and that will give me 30,240 available PIN codes. So 30,240 available. But now what we have is we have a situation where they say, once you've chosen a certain digit, so once you've chosen 0, there's nothing stopping you from choosing 0 again. So especially here with PIN codes, you can easily go and you can make your PIN code 11111. You could repeat that one as many times as you like. So because repetition is now allowed, we have to now go and reinvent this a little bit. When I say reinvent this a little bit, when we initially started this, I showed you a tree diagram. And on the tree diagram, I said to you, once the first choice is made, you don't have that available anymore. So that's why it would become 10, then times 9, times 8, times 7. But if we keep on using this idea, then we actually realize, but if I have 10 choices available on the first press of the PIN pad, then I still have 10 choices available on the second one. Still have 10 choices available on the third one. So in this case, there's no factorial, because remember, factorial starts with a certain number, and then it goes down. It goes 10, 1 less, 9, 1 less, 8, 1 less, 7. So this situation is not a factorial. This one pretty much says we are going to have 10 options on the first press of the PIN pad, but we're still going to have 10 on the second one, still 10 on the third one, still 10 on the next one, still 10 on the next one. And obviously, we've said this before, the counting principle requires us to multiply, because we're going to say I have 10 by 10 by 10 by 10 by 10 available codes here. So this is why you could do it manually like that, or the other option is just to say I have 10 to the power of 5 available choices. And obviously 10 to the power of 5, that is 100,000. So 100,000 possible choices. So please be careful. We are not always going to use factorial. Factorial specifically refers to the fact that once a certain choice has been made, it's no longer available, meaning repetition is not allowed. So if repetition is not allowed, we can use factorials. But if repetition is allowed, we actually end up using exponents. So let's put that into proper terms. So one of the first questions you're going to be asking yourself when you look at one of these counting problems is you're going to ask yourself, is repetition of elements allowed? So if you say no, repetition of elements are not allowed, then you're either going to use the factorial, that is if all the elements are being chosen, or if you don't choose all of the elements, you use that in permutation R, which if you think about it, that is also a factorial. But if repetition is allowed, we can't use these factorials anymore because they click over. Remember, they go 10 and they go 9 and they go 8 and they go 7. And in this case, this doesn't happen simply because of the fact that we are again allowed to use the same we used in the first choice and the second choice and the third choice. So if we say yes, the repetition is allowed, then what we're going to be doing is we're going to be saying it's n to the power of R. So just to remind you again, n is the number of available choices I have. So if you recall, with that PIN code, we had 10 digits available. So every single time I pressed the PIN pad, we had 10 options. So that is the number of available choices on every single PIN pad, on every single choice. That doesn't make a lot of sense, but I hope you understand what I'm saying. That is the number available on every single choice. Whereas this one is the number of times you have to choose. So R is the number of times you have to choose. So specifically here, we have 10 digits, and I'm going to go and I'm going to have to choose 5 times. So that's why it's 10 to the power of 5, which is exactly what I did over there. 10 times 10 times 10 times 10 times 10, which is 10 to the power of 5. 10 choices available, making 5 choices. Well, I should rather say 10 elements are available, and I have to choose 5 times. That's pretty much what it is. Okay, so please just remember this difference. If repetition is not allowed, then we use a factorial or a permutation. If repetition is allowed, then we can no longer use a factorial or permutation. We have to go for an exponent. Okay. Then the second one that can get kind of tricky is, are the elements unique, or are some of these elements exactly alike? So let's quickly go back to one of those word problems that we did in the previous video. How many words, and I've explained to you guys that these words, it doesn't have to necessarily make sense, it just has to be a different arrangement each time of the letters. So how many words can be formed if you use all the letters from the word maths? Now, if you look at that, there's 1, 2, 3, 4, 5 letters, and none of them repeat. Now, I don't actually want to use the word repeat, because repetition means you can use that A and then you can use it again. So it's not really about repetition. I should rather say all 5 of these elements are unique. They don't look the same. Okay, so because they don't look the same, we can then go and we can say, okay, I want to go and choose from those 5, so I can just go 5 factorial, because I'm using all of them. So let's just quickly focus here. I'm using all of them, number 1. I'm not allowed to repeat any of them. So the moment I say I'm not repeating, we just said it there, if I'm not repeating, this is a factorial. And it's not a permutation. Why? Because I'm using all of the letters. I'm using all of the letters. So I can then go and say this is then going to be 5 factorial, which ends up being equal to 120. Right, but now, how many words can be formed if you use again all the letters from the word statistics? Now, the issue with the word statistics is the following, and this is not about repetition. I'm not repeating any of the letters. But if I look at these letters, you will realize I've got 1, 2, 3 S's. So that's not repetition, it's just the fact that 3 S's were given at the beginning. So I'll write it down over there. I've got 3 S's. Then I look at the T's and I say there's 1, 2, 3 of those as well. So I've got 3 T's as well. And again, it's not about repetition. You can't use it as many times as you'd like. It's just that those 3 T's, they're identical. They look exactly the same. So it's not repetition, but does it really matter if I go and I put a T over here and a T over there, and I swap them around? With that change, do they still look exactly the same, or is it something different? It's the same. So that's why whenever you deal with these elements that look identical, it means we can't have as many arrangements with identical elements as we have with unique elements. That's pretty much what I'm trying to get to. Okay, then you'll see A is unique, so there's only one A. I, however, repeats again. It's 1, 2 I's. And then C is also unique. So this one specifically is something you can kind of learn off by heart. When you want to go and you want to make these arrangements from the letters, and all the letters specifically in the word, the first thing you do is you count all the letters. You say, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of them available. So let's just double check. Yes, there are 10 letters. So however many letters you have available, you say that's 10 factorial. Now, this would have been a valid answer had all of the letters been unique. So if I had 10 different letters that all look different, then that would have been my answer. Done. Finish. But because there are 3 S's, those 3 S's, not repetition again, but those 3 S's look exactly the same. Meaning, whether I write the 3 S's like this, whether I then swap them around and like put that one over there, or I swap them around and put that one over there, it's the same thing over and over and over. So I can't actually go and say that there's a change in swapping those S's. So I have to go and now eliminate some of the arrangements that happened here that would have been valid had the items been unique, but is now no longer valid. And in factorial, to cancel out this, I'm going to simply do this. For each group that is not unique, so the 3 S's, I will then divide by 3 factorial for the 3 S's. But there are 3 T's. So I will also divide by 3 factorial, and that 3 factorial represents the 3 T's. And there are 2 I's, and because also those are not unique, I'm dividing, I know I'm multiplying, but I'm dividing because it's in the denominator, I will also multiply by 2 factorial. So literally every single group of letters that is not unique, there needs to be divided by. So that comes from the 3 S's, that comes from the 3 T's, and that one comes from the 3 I's. So you just have to go and look at your little groups and make sure you divide by that. So that's pretty much what you do. So if I then go and I put this into my calculator, it's 10 factorial, over 3 factorial times 3 factorial times 2 factorial. And that is going to give me 50,400. Which, by the way, is a lot less than it would have been if I just got 10 factorial. So if the letters were actually unique, if I had 10 unique letters in this word, then I would have gotten 3,628,800 possible arrangements. Okay? But because they are not unique, I then go and divide by these little groups, and then I only have 50,400 possible arrangements. So this is something, a very common question that you kind of have to get used to. Okay. So here's a little summary. We have to ask ourselves, are the elements unique? If I say yes, the elements are unique, then again, if repetition isn't allowed. So if repetition isn't allowed, I can then just go and I can say it's in factorial only, or I can say it's in permutation R, depending on the problem. But if the elements are not unique, so if there are any elements that are not unique, you will then have to go and you will have to write it's in factorial, and then what you have to do is you have to make little groups of those items that are in fact not unique. So you will have to go and say, let's say the groups, little groups, you say there are 3 of a kind that look exactly the same, then over there you'll put that 3 factorial. If there's maybe 4 of a kind that looks exactly the same, then you will go over there and you will say that's 4 factorial, and so forth. So for every single group of elements that look identical, and because they look identical, again, it's not that I can repeat them, it's just that I have these elements that when I arrange them, they don't seem to form a brand new arrangement because they look the same. So for all of these little groups, I will then just create one of those factorials and I will divide by those factorials. Okay, so obviously this is an example. This isn't every single time going to be 3, 4. It just depends on what this is then going to go into those factorials. Okay, so that is pretty much the first 2 questions, the first 2 changes we have in this counting principle. So thank you very much for listening. There's going to be another video on some other changes we can make in this counting principle.